Welcome, everybody. Welcome to our CRE.A.T.E UTC workshop. My name is Shijun Jeff Shi. I'm the Technology Transfer Officer for the CRE.A.T.E UTC Center. I'm also an assistant professor at Texas State University. So today we are very pleased to have Dr. Chunyu Qiao from WJE to give us a full day workshop on concrete petrography and image analysis. The workshop has a morning lecture session, which is starting right now. We will also have a hands-on training session in the afternoon at the shared research operation at Texas State. So before we get started, I want to thank CRE.A.T.E UTC Center, the shared research operation at Texas State University, and also New Mexico Department of Transportation for co-sponsoring this event. I will give a very brief introduction of Dr. Chunyu Qiao. Dr. Qiao is a senior associate and petrographer at WJE. He's an associate member of ACI committees 201 concrete durability and also ACI committee 365 service life prediction. He's a junior editor and board member for Journal of Infrastructure Preservation and Resilience. Dr. Qiao received his PhD from University of Science and Technology, Beijing, China. He was a visiting scholar at Purdue University from 2013 and 2015, and a postdoc researcher at Oregon State University from 2016 to 2018. His research interests include microscopy of cementitious material, transport properties of cementitious material, chemical admixtures, and concrete durability. So without further ado, let's welcome Dr. Qiao to give us a lecture titled Concrete Petrography and Image Analysis. The what, why, and how, that's the title of the lecture. The lecture has two parts. Each part will take around 40 to 45 minutes, followed by a quick Q&A. Then we'll have a short break in between, and we'll start the second part. So let me stop sharing these slides, and I'm going to share Dr. Qiao's lecture slide. Let's see. All right. All right. So the floor is yours.
Okay, sounds good. Thank you very much. Yeah. Well, thank you for Jeff's warm introduction to my 2 hours presentation. I am Joe Qiao from with Jenny Elstner Associates. I'm working in the Austin office. I'm a petrographer. I have been a petrographer for like probably 5-6 years since 2018 after my postdoc study. So it has been fun, to be a petrographer. So it is very specialized, unique, let's say examination or tools for forensics. So I really appreciate this opportunity to interact with everybody here to talk about petrography, what it is, how to work with petrographers, and what can we provide, for engineers, consultants, or other clients and customers. And also, to give some, insights into how we do petrography and what are the principles. So today, I think I will just talk about my presentation will divide into 2 sections. The first section will be a general introduction about what petrography is. And the second section will be like, I will throw out several case studies about real projects, during consultation in the years, and to give everybody an idea how we work in the lab and how we interact with, clients, engineers, and attorneys, owners, contractors. Finally, I'll close with some limitations or futures in the outlook of petrography, and also what's the limitation for petrographies and how we can improve from it. So my presentation will be divided into the several small sections, as I mentioned. What and why is concrete petrography, and how to work with petrographers, and what can concrete petrography do, And case studies of petrographic examinations, that will be a second class, and future concrete petrography limitation and closing remarks. So what is petrography? So this is not really a new term by any means. So, construction industries borrow this idea or method from geology. So petrography in geology is a branch or study of the science of petrology. What is petrology? Just like geology, we look at rocks, we look at minerals. So petrology is to use microscopes or other techniques to characterize the mineralization composition of rocks, the texture of rocks, and to back analyze the formation, other information about the rock during the formation and the deterioration. So petrography involves heavy or detailed description of rocks as minerals, as I mentioned about. And the petrographic analysis involves, microscopic observations. For example, when you have a sample from the field, you have first observation by your eyes or the feeling or the smell or anything, handy, with your eyes or other, handy tools. And after you bring your samples back to the lab, so we can prepare samples, to make thin section, polished sections, or SM sections. So with different techniques, so we can use different microscopic tools to look at them, like stereo microscopes, petrographic microscopes, and even scanning electron microscopes. And we call these people ourselves petrographers. So here I'm just, the two, my presentation will heavily, rely on images. So there's a way, we call ourselves petrographers, not photographers, but we do share some similarities because, petrographers use microscope to take images and photographers use cameras to take pictures, but we all focus on details, the information behind what you're going to take. So the photos I'm showing case on, on the right is like the thin section photo from a rock. So you can see that's like a basalt rock. So you see the feldspar crystal in a amorphous matrix. So I can give you a lot of details about this, but this is just like a introduction. So we can talk about that later if you have any questions. So what is concrete petrography? Concrete petrography, basically, we just apply the principle of petrography on construction materials. So we call concrete, man-made rocks. So that will give us some access to the tools from geology to study construction materials. So, literally concrete petrography, this whole topic or study started from 1930s. Back then, Caltras engineers they noticed some abnormal deterioration on a bridge. So later on, the problem, was confirmed as alkali-agar reaction. Basically, back then, that's alkali-silica reaction. So back in the 1930s, 40s, people started to use microscopes or petrography to look at concrete. So for us, we will do, we normally have to do a very detailed job, a good job to detailed description of the condition component of concrete or any construction materials. So also the analysis involved hand sample observation by your eyes or other handy tools on site, on job site, or just when you log in or receive the samples, and also after the lab preparation. So we will have lab surface or section, we'll have thin section, we'll have other, polished sections for different levels of microscopic observations. I will lay out the details in the following sections. So we call ourselves concrete petrographers. So, just from the name, don't get misled that, oh, we only look at concrete. So we can look at anything that can be used, in construction, in structures. So we can look at that at dimension stones. We can use petrography to look at grout. We can use microscope, petrography to look at mortar and other cementitious material or binder systems. So these two images on the right, showcase a very standard. I don't want to say very standard is a low carbon footprint concrete, that was placed like 80 years ago in a dam. So in this images, this is showing the cementitious material matrix. The green arrows indicates, I think that's the B-light particles, from the cement. We all know, cement consists four major phases, A light, B light, eliminated ferrite. So ferrite, reacts really quickly in the first few days. So you normally don't see those things remaining in your cementitious material system. And A light also reacts really, really fast in the first few days. So you don't really see that. So normally the abundant unhydrated particle or phases from cement you normally see in a mature concrete sample is B light. And the yellow arrows there indicate, I think, slag cement. So those slag cement particles, they're very angular. And in those two light modes we're talking about here, the top is called plane polarized mode. The lower is a cross polarized mode under microscope. So in the cross polarized mode, so it's totally, it shows total distinction to show its amorphous nature of slag cement. So the tools. So what are the tools? First tools we're talking about for petrographers are our eyes. So we have to be very sensitive to the different features or subtle characteristics in samples for different projects. That we call the beginning of the examination from when we receive the samples. After we have the first round or login sample or receive sample and inspect it visually, we will ask the technician in the lab to prepare samples in different ways or unique ways we want to examine. So the three major tools or microscopic tools we use in the lab are laid out in those three images on the right. The first on the left top, that what we call the stereo microscope, is a reflective microscope. So we use that to look at the lab sections. After your sample is labbed, you will review a lot of details about the features or characteristics of some material or materials you are going to look at or examine. The one in the middle, we call that is a petrographic microscope. So we use that to examine thin sections. Thin sections, by the name, is a really thin slice of concrete or material you're going to look at. So how thin it is 1 mil thin, like 25 micron thin. So the light can go through your material. So by doing this, we can look at the thin section in a very detailed way up to 600x under different light mode or conditions to examine different aspects of the material. So the right bottom one, so everybody probably has seen that in material characterization classes, or you may have already used that. That's the SEM. So that's benchtop SEM. Normally we use that in some very specialized jobs to look at the chemical composition or very detailed evidence of different mechanisms for deterioration. For example, delayed etching-night formation, because we want to look at the etching-guide nests. They are like several or multiple like micron, small or big. So normally optical microscopes cannot really see that much in detail. So you need SEM to look at under, let's say, 1,000 times or 2,000 times or even higher. So those are the three major tools we use, but we are not limiting ourselves to, just to look at concrete microscopically. So we also use other material characterization tools to assist our, observations or forensics. So other normal or regular tools we normally use first, we can measure the hardness of the paste. So we use Mohs hardness index. And we can also categorize or describe the different colors of the paste or some material. So that's we can use color chart to do that. And also we can do different kinds of chemical analysis, for example, elemental analysis for your materials. If you have chloride problem, de-icer problem, seawater problem, and coastal structures, you want to look at the chloride profiles. And if you have, high sulfate soil condition in some underground or below soil line structures or foundations, you want to measure the sulfate ingress as well chemically. And also you can use, X-ray diffraction to look at any, alteration minerals or phases in your cementitious material compared to the unaltered ones to see what is a mechanism or what is a progress of the deterioration in different scenarios. So, from my understanding as a petrographer, petrographic analysis is really, assisting tools for engineers or our clients, from the lab to tell them or help them determine or decide what's has happened to their either new construction or their existing structure conditions. So the knowledge or, the aspects, we normally use or apply in our petrography analysis is really a combination, let's say, geology, knowledge, concrete construction, concrete structure, basics or fundamentals, and material science. Geology, there's no more to say. The whole idea is borrowed from geology. So we need to understand, as a petrographer, you need to understand some basic information or knowledge about rocks or minerals, because 70% of the volume concrete is aggregate. What is aggregate? Aggregate is different size of rocks. Either is a natural gravel, or it's a crushed aggregate, or it's manufactured sand, or it's natural sand. So they're all from the nature. So they're all different kinds of rocks. So different forms, different characteristics, either physically or mineralogically, can make a difference to the workability or constructability or even long-term performance of concrete. So of course, you need to know geology. And we are construction industry. So you have to know the basics about the concrete materials. So, and also the concrete construction, especially when you troubleshoot some issues for new constructions, because normally they have, slow setting, low, like early age freezing and low strength, and also other, issues or difficulties in, placing, finishability or constructability. You need to know some information or knowledge about, mixing, batching, handling, placing, curing in different techniques, different tools we use from different ACI or other, industry guidelines or codes. Also, we, as a part of, structural forensics, we are a team player in the lab. So you have to know some basics about concrete structures, especially, different structure, different dimension, different exposure conditions can make a huge difference about the performance of concrete, even though it's the same, constitutes or similar constitutes. So you need to have a basic understanding, at least, the design of the structures, the formwork, how they, how they constructed the structure, and what's reinforcing layouts, for flat works, what is joint, design, and what are also other, contraction or other, dowel bar design, those kind of basic information, especially for pavement, sidewalks, or driveways. And also, we heavily rely on material science. That's the basics or fundamental for our laboratory examination. So as a scientist, about cementitious material, you need to know cement chemistry. You need to know something about some information about hydration, how cementitious material, hydrate. Before we have to know hydration of cement. These days, people talk about low carbon footprint concrete. So we have to do so many different kind of alternative cementitious material or SCMs or alternative SCMs into our current or modern days, modern concrete design. So how those, components play a role in hydration or reaction with cement or with other material, that's very critical too. So, a lot of times, forensics, you have to know how your concrete deteriorates. So that involves some knowledge about concrete durabilities. I would recommend to you guys, if you're interested in concrete, durability, I would strongly recommend everybody to check out, or at least to get quick look about ACI 201, the Guide to Durable Concrete. That's a very, very good resource and document, in industry to talk about almost all the aspects of concrete durability. So that is concrete petrography. That's the background of concrete petrography. What is a petrographer and how to work with petrographers. I'll just use a few slides to lay out. As I said, we are a team player for the whole forensic team or investigation or projects. So a comprehensive petrographic analysis requires teamwork, from different aspects of the construction of structures, from the material supplier, from the contractor, from the owner, from the maintenance tool, team, and also from, forensic engineers. So it is not a puzzle like, clients throw out some samples to us, tell us, hey, tell me what you find and what is wrong with my concrete. It doesn't work like that. So it works like the more information or background information you provide to us, the more we can provide to you by knowing more about what has happened on site and on, to your structures. So, some major information we want to get and some major information we want to hear or communicate with, with our clients or different parties, include, let's say, what is on-site conditions. If you are talking about some problems on site about your structure or construction, and also how old is the concrete. So what is the construction dates, or what are the ages of different the concrete members or structural members. And also we want to know something from, specification of the design or construction, any specs, any make designs, submittals, any specific construction curing methods, that can help us, especially for, investigation on new constructions. And also, we want to know any record, for example, any field reports from QC/QA teams and any batch tickets from material suppliers and so on and so forth. So here, I want to use 6 different images to just give us a kind of workflow how we play a part in engineering or structural, investigation or forensic investigation. So everything starts from the top left. So let's say you have a dam. So here it is a dam, is a generation station, it's a dam. So it's a dam somewhere in Canada, I can tell you. So you see this dam has a lot of cracks, deterioration, some spalling, some white efflorescence or whatever you call, exudate, oozing out from the structure. So it is, critical condition. It is critical infrastructure for the local community. And the engineers or the government or the agency, they want to know how safe the thing is and how bad this deterioration has, progressed. So, the owners, normally they will call, engineers, they will call some engineering teams to give, let's say, engineering on-site inspection. So a lot of times, I can tell you this is ASR case. So this whole structure has experienced ASR deterioration for decades. So you can see in the middle of the image, so the engineers normally have to do a very detailed on-site inspection about different parts, what's the condition of the whole structure, of the concrete structure, so on and so forth. So this investigation has been ongoing, or this routine inspection has been ongoing for decades. So engineers have constantly give, advice to say ASR is a internally expansive reaction, right? So the whole structure, your concrete shell or a concrete member, they are trying to expand. So you want to release this expansion. How do they do that? Since engineers try to say, okay, let's try to give some saw cuts to saw cut, some slabs or some members to release the stress. So you can see that's a, hemispherical like hole over there, but that's like back to 40 years ago. That's a circular, that's a concrete cylindrical core. So after 4 decades or 40 years, keep cutting. So you can see how much expansion that has occurred, how much expansion they try to eliminate just in that structure. It was a core hole, it's a spherical. Right now, it's half spherical. So that's the on-site inspection and some, routine inspection. Also, we want to do some, microscopic or petrographic analysis to document the current condition of the concrete after so many years. Normally, we get a core, like I said, after we receive a core, we do a visual inspection on the condition of the core laid out over there. Also, as I mentioned in the previous slide, we want to further prepare the samples in the lab. That's the lab section images, on the bottom right over there, follow the red arrow. So we see some features there. You see an aggregate particle, right? And see an aggregate particle, there's a crack, getting, extended from within the aggregate particle to the paste. And you can see those microscope, those micro cracks, they are filled with some white stuff or some secondary deposits, we call that. So that is ASR gel, occupying, ASR associated micro cracks from, reactive aggregate particles. That's a very standard feature of ASR on polish section. Also, we want to know the nature of the rock. So we want to know what are the reactive components in this concrete. So only based on the color on the left section, that cannot give information to justify or determine the aggregates type in this investigation. So then we want to use the thin sections, as I said. The thin section picture is in bottom middle image. So you can see in that aggregate particle, you have a lot of very, very fine, coarse grains. Those are reactive particles. That's, I think in this case is a chert or some rhyolite components with, amorphous, siliceous matrix or some coarse grains that really, really fine, which can be reactive in a high pH condition in concrete. So that's a very typical thin section observation for ASR jobs. And also we want to judge, we want to know, so this structure has been here for decades. So is this reaction new or is this reaction old, or how long it has been there? So even though we cannot accurately date back the timeline of ASR reaction, but based on the chemical composition of the gel, actually that can give us some idea how old the gel is. So chemical composition or elemental composition of the gel cannot be analyzed by only optical microscopes. So then we use SEM scanning, electron microscope. Normally they equip with some, EDX is an energy dispersive, spectrometry. So that technique coupled with SEM can give us ideas about elemental mapping of different components. So in this case, we can see in that SM image on the bottom left, so you see different strips or different colors of contrast in this ASR gel. The ASR gel is something in the middle, like the gap. That's the ASR gel in a concrete sample. So that shows some elemental, variations even within the gel. Some zones are calcium rich, some zones are, alkali rich. That tell us the gel probably has been there for a long time. So all this observation from the lab, from the eyes, from the microscope, from SCMs, we formulate reports, we formulate different detailed descriptions about condition concrete feedback to the engineers. So let them to understand or better understand the current condition of the material condition or the ASR progress, and let them make decision for the future maintenance or plans for budgeting or whatever, that will work with the agency or the stakeholders. So we always just call ourselves like, the lab eyes of the engineers. We are the extended eyes of the engineers in the lab. So we just do our job under microscopes, and engineers do their job from the site observations and other structural analysis. But at the end of the day, so we want to formulate a very informative and accurate, description or condition assessment or other purpose, to the stakeholders. So that's basically all, the workflow for how a concrete petrographer works with engineers or other stakeholders on specific jobs. So what can we do? So petrographers, we can look at almost, I don't want to say every aspect of the material, but most aspects of the materials in different ways with different emphasis for different projects. So like I said, we work very closely with engineers. For different projects, you will work with different clients. The clients can be owners, can be contractors, can be material suppliers, or for some litigation support or some litigation cases can be attorneys representing different parties too. As a material scientist or engineer, petrographers, we have our current testing lab tools. We have ASTM standards. We have AASHTO specs, or we have other industrial codes or guidelines as our, let's say the measuring sticks for different cases, or the tools for different, petrographic examination or investigation tools, and also over the development of new technology over time. So, new technologies emerges, in the lab, so we can try to incorporate some new techniques, with current standards or standard testing tools to better understand or better document or describe the problems in the lab. So some new techniques, I don't say new techniques, but they are not haven't been standardized, but has been, have been used, in the lab. For example, we use fluorescent microscopy. So we can use some image analysis, especially these days, AI is or machine learning or image analysis are really hot topics, as the computing powers, dramatic increases and the cost, dramatically decreases. And also we can use some electrical resistivity measurement to assist to evaluate the transport properties or the quality of the concrete. So what are our major, let's say, weapon tools, for petrography in the lab? So the major one in the middle, we call them ASTM C.R.E.A.T.E. So that's a standard practice for petrographic examination of hardened concrete. And also, up in the north, not probably necessarily in Texas, but up in the north in the mountain states. So free-thaw damage or any de-icer damage are big topics, are major concerns, especially for DOTs or other flat work, stakeholders or parking structures. So to properly evaluate or determine the hardened air voids parameters are very important because air entrainment is a major tool to fight against free-thaw damage. So ASTM does have a specific standard, we call that ASTM C457, to determine the parameters of the air void system in hardened concrete. So this is not plastic air measurement when you have a job on site. This is hardened concrete air void analysis using microscopes. And also, like I said, we can use SEM to look at concrete. So there is a ASTM standard to examine concrete using scanning electron microscope, which is listed on the right. That's the ASTM standard C1723. So in addition to those three, actually we have another ASTM standard specific concrete aggregate examination that's called ASTM C295. That's a petrographic examination of concrete aggregates. So those are the major guidelines, or basis for us to use in the lab. And what question can we answer? So what projects can you work on, basically? So every time when people look, ask me that question, I normally characterize three major, let's say, domains or aspects for concrete petrographers, what we can do. The first is the concrete quality or regarding concrete construction. What's ratio issue, slump issue, cement issue, air issue, or whatever. So for those new construction, issues, a lot of times, a lot of those aspects has been documented or, specified in ACI 301. So that's a specification for concrete construction. The major aspects, discussed in that document, we can petrographically examine under microscopes. And also the second major domain petrographers can work on is the surface defects. The first surface defects can be regarding to, construction or finishing problems or long-term durability problems. But for flat work, construction, a lot of those aspects have been well documented in this ACI 302 Guide to Concrete Floor and Slab Construction, majorly for flat work surface defects. And also, like I said, for existing structures, durability is a big concern. So ACI 201 Guide to Durable Concrete. So the major, durability aspects documented or listed in ACI 201, petrographer probably can, examine under microscope. So what do we look at on using microscopes when you do a petrographic examination in the lab? So what do we look? So what are you looking at? It's like you have a sample, and how do we start? So basically, we start from the components of the aggregates. So we all know the four major components in the concrete. First is coarse aggregate, of course. Second, fine aggregate, right? And third is paste matrix. The fourth is air void system. So for the aggregates, a lot of times we start from the physical characteristics of the rocks or the aggregates, and then we go to mineral assembles or the properties of the rocks. For example, we will examine the gradation. So to see if the aggregates are gap rated or not, because if you have gap rated concrete, you will require a high higher volume paste to cover it. So that normally means your concrete's workability will get impacted and your shrinkage will get impacted as well. And second aspect, we'll look at distribution of the aggregate to see if you have any segregation issues. So if you have a segregation issue, that will have different reasons or different aspects of problems you will get. And also the shape. What are the shapes of aggregates? The shapes, angular aggregate crushed rocks or the rounded natural gravel, they have totally different water demand or workability, performance. So what are the shapes of aggregate? Are they consistent with the design or not? And also the mineralogy. So are you supposed to be non-reactive aggregate against ASR or AAR, or do you contain any reactive aggregates or not? So those are major aspects for aggregate examination during a petrographic examination. And also, we pay a lot of attention to paste matrix. Of course, that's where everything gets binded or bound together, make a whole, make it like a rock, as of concrete. So we'll evaluate the cement hydration to look at if there's any curing issues or any surface curing or internal curing issues. So we'll look at what's the composition of it. So does it contain any supplementary cementitious materials or alternative cementitious materials to like the nature of the paste? And also a major aspect for petrographers, a lot of times it's very critical for us to give an estimation of what to cementitious material issue, WC or WCM. So when I say that it's an estimation, because it is very, very difficult to give you a very accurate, WC or WCM, estimation or evaluation, because there are so many actors can play a role to give you difficulties to properly assess it. But a good petrographer should be able to identify a proper range for it. And also, as I mentioned, probably not really relevant to Texas here, but up to the north in the Midwest, in the mountain states, the air voice system are very critical to fight against the winter weather or condition over there. So we will evaluate if needed, for example, air content, the spacing factor specific area of the air voice system. We call that the distribution air voice. And we will also look at it if there's any consolidation issues. That's important for construction or the integrity of structure. So if you have a stick mix, you have low slump, sometimes consolidation can be a major issue, honeycombs or any other defects like that. And also we'll look at the embedded objects. Of course, most of the structures we talk about are reinforced. So we want to look at either is rebar is steel reinforced or fiber reinforced or any other reinforced or any other objective, embedded objects. For example, if you have steel rebar reinforcements, so what's the cover, what's the thickness, and what is the corrosion condition, especially for corrosion issues for old structures. And also the synthetic fibers, are they distributed well, or do you have conglomerates or any features like that? Also, as I mentioned, surface defects is a major aspect for flat works, parking garage, pavements, sidewalk, driveways, floors. So we'll look at any problems, about in finishing or coating or spalling or flaking, those surface defects. And for deterioration patterns, that's also we pay a lot of attention to. So because a lot of times, if you have good concrete, good structures, you don't call us. You don't call petrographers because, you only call, consultants or petrographers because your structure has some issues. So when you have some issues, it is our job to properly and in detail describe or document what's the cracking pattern, what's the deterioration pattern. It could be cracking, it could be spalling, it could be delamination, or any other forms of distress or damage. And also a lot of durability problems. It has some involves the chemical reaction or mineralogical, let's say, alteration between the external or environmental substances and the cementitious materials. Then involve some secondary deposits or some alteration. The most well-known one everybody knows, concrete carbonate. So the carbonation depth, you have as a petrographer, you have to pay a lot of attention to it because that relates to corrosion. And also we look at etching gate. Etching gate can be a problem or can be a problem if we're talking about delayed etch gate formation. or it can be an indicator for high moisture level. So as of any water structures or structures in contact with soil or water. And another thing, another secondary deposit we pay a lot of attention to, as I mentioned a few times, is an alkali silica gel. Basically, we call that ASR gel. Is a major reaction product for ASR deterioration, and gypsum for sulfate attack, or calcium oxychloride, that's for deicer damage. With all the the component characterization, the surface condition assessment, the distress characterization, and the secondary deposit evaluation. So for projects involving or regarding construction, so we can verify mixed design on the right. So we can look at aggregate, we can verify the components are consistent with mixed design or not, and we can estimate, compare the actual Watson ratio estimation to the specified Watson ratio, and we can also evaluate air entrainment is insufficient or insufficient. For mixing, like I said, do you have any insufficient mixing issues? Do you have any retempering issues? Do you have any consolidation issues? Segregation, that's handling, placing, constructing. And curing, that's a major aspect, especially for hot weather concreting or cold weather concreting. So do you have, proper curing or insufficient curing? So do you have any plastic or drying shrinkage cracking, or do you have any early thermal cracking or not? And also, because of insufficient curing, do you have any restricted hydration, and so on and so forth? Other aspects could be, for large dimension structures for mass concrete, do you have any thermal cracking, or do you have any concern from the hydration heat accumulation or gradient, in large dimension structure members? So for construction aspects, I just listed the major points here, but what we can do, are not just limited to these items on the right. So again, a lot of them are well documented in ACI 301. So for surface defects, we'll look at if you have random cracking. So a lot of time there are shrinkage cracking or some thermal cracking, or do you have low wear resistance? Probably you have some lintons, you have some weak surface or dusting. So we look at those aspects. And also scaling is a major issue again, in the north part of this country. And pop outs near surface ASR in some indoor flooring systems, because accumulation of the water or alkali near the surface of concrete, so you will have some near surface ASR or pop outs we see. Also blistering, that's also flooring system. You have any delamination, for example, if you have trowel, air entrained concrete, so sometimes you deplete the air of the near surface, and you will alter the bleeding of the water, get it trapped beneath the surface, give you the delamination. And also spalling, different kind of spalling. And we will also look at discoloration or staining on the surface. Why are this happening? If you have shallow aggregates or some mortar flaking. And also during construction, rain damage can be a problem during construction. Let's say you're placing pavement, and all of a sudden a thunderstorm comes in during the construction placement. So that will alter your property of that will change your construction, let's say, schedules, and also alter the surface properties or placement or difficulties of the structures. So everything about surface defects, I think you can find most of them in ACI 302. And the third major topic or aspects we look at as petrography in the lab are concrete durability problems. So different aspects, as I said, we can look at first, free thaw damage up in the north, not here, but sometimes in north part Texas, you may run into this problem too. And alkali aggregate reaction. So you have alkali silica reaction, you have alkali carbonate reaction, or these days in the New England area in this country or part of Canada from some specific quarries. So you have some rocks containing some, iron sulfides, which can be oxidized, in the concrete, give you some other, aggregate reactions, and which can be a problem in specific regions, not here necessarily in Texas, but for example, Connecticut, Maine, those states. Also, some very specific chemical, sulfate attacks. External sulfate attack, like I said, in Southern California, the soil is normally high in sulfate, or some part in Colorado. So if you have a sulfate salt ingress into your foundation members, so you will deteriorate your concrete. So we call that external sulfate attack. We can look at the features microscope petrographically. And another not common, but sometimes we come across with, we call the internal sulfate attack. Internal sulfate attack, a lot of times it has another name, delayed edging guide formation, which is short for DEF. For specific chemical reactions, it could be different exposure conditions. Let's say seawater coastal structures, you have chloride problems and corrosion problems, and acid attack in some specific industrial structures. And you have some freshwater problems, let's say some tunnels, some water treatment plants. And you have carbonation, for some indoor parking garage or structures with, high CO2, or just regular, natural carbonation. And also de-icers or de-icing damage or anti-icing chemicals that can damage or deteriorate concrete. We can look at that under microscope. And also some other industrial chemicals, sometimes you just run into different very interesting topics, and different chemicals can have some interaction with concrete. We can look at that. And also MICC, microbiological induced concrete corrosion. So basically is some acid producing bacteria in, those kind of environment in wastewater treatment plants, tunnels, manholes. They have some bacteria producing acid, which can corrode your concrete pipes or other structures. So we call that MICC. We can look at those kind of crack, damage, cracking or deterioration of the material itself. Also, physical salt attack and so on and so forth. Again, major, most, all of that, has been well documented in ACI 201. So how we interpret concrete, let's say. Here, I just start to show some, routine, I don't want to say routine, just like some basic examination we look at under microscope or, from the material, how we start, how we do, petrographic examination in the lab. Again, so we start from the most abundant component in the concrete, coarse aggregate. So for this coarse aggregate, we will look at, like I said, we'll look at the distribution. We'll look at the gradation. Here you can see that's a very typical Texas concrete, with limestones, with some river gravels. You can see the aggregate has, is evenly distributed over the place from the depth over the length. So there's no grade segregation issue. It's a well distributed, it's a good quality concrete. So you can also look at the size of the particles. So they are well, let's say, graded. So there's no gap grading issues. When I say gap grading issues, means you have some top size aggregate and you lack some intermediate, size particles, and then you have a whole bunch of fine aggregates. So we call that gap grading. So, but this concrete, you can see you have top size, probably, I think this is like a 3/4 inch, and you have some, half quarter, you have some 3/8, you have some number 4, number 8, that's a very well graded, limestone, crushed limestone and aggregate in this area. So that's the first aspect we look at from your eyes or from microscope. And also, we will also look at, let's say, is this natural gravel or is this crushed rocks? They, of course, they look very different, right? So for natural gravels underwater, in the river, crushing or water, weathering. So you don't have a lot of sharp edges over, thousands or millions of years. So you see a lot of round particles. So here on the left, that's a natural gravel. So I think this aggregate, this concrete is from somewhere in Arizona. I forgot. So that's a chert particle, actually. That's the one on the left. You see that's very angular. That's very, very angular rocks. So, and the color is kind of uniform. So you can tell that, of course, that's a crushed rock. I can tell that that concrete is from South Dakota. I forgot where. Actually, I cannot tell you where, but that's like I think that's some red marble. No, right, dolomite and some sandstone over there. So you can see the natural gravel and crushed rock stone, they are very different, in, visually or in characteristics. Also, we can also look at the mineralogical composition of rocks. So here are two images. On the one on the left, so you can see that's a limestone, you know, basically here in Texas, that's limestone aggregate. And the one on the right, that's that's a concrete sample from Colorado, so which is rich of siliceous rocks, which is granite over there. So visually, they just look very different. And for the sand, so the first thing we need to tell is this manufactured sand or is this natural sand? So those are the pictures. The picture on the left, that's a, manufactured sand. I believe that sample is from Costa Rica. Because there they just have a lot of, limestones, from the beach or from their mountains, or they crush the rock to make manufactured sand. They're fairly angular and also, kind of uniform in color or look. The one on the right, that's a natural, Colorado River sand, in Texas here, Central Texas. So it's basically siliceous, a lot of coarse, particle fragments. You have some granite particles there as well. Sometimes you have chert. So those are the aspects of concrete aggregates. So the paste. So when we look at the paste, I will throw out some pictures here. So for the paste, first the color is different, right? So, cement normally is dark. So the more water you add, the higher the water content is. Your paste, after you mix it, it will tend to be lighter and lighter in color. So the first aspect petrographers to look at is the concrete color, the paste color. So you can see one on the left is much darker compared to the one on the right. And also it's much harder than the one on the right. So that is a very vivid or first signal to you, okay, you have a low Western ratio concrete and you have a high Western ratio concrete. So when we switch the tools from the stereo microscope from the lab sections to thin sections, you can look at more details about the unhydrated cement particles. So the one on the left, that's a very standard, almost a little bit, old concrete, Portland cement concrete. So you see the light blue particle over there with that like a cluster of like a grapes or whatever those features. Actually, those are a whole bunch of B-light particles, intersected with ferrite. Ferrite is normally because they have the iron. Sometimes they can be a little bit dark or red in thin sections. So you see, we call that grapes or cluster of B-light with ferrite. So the one on the red arrow on the bottom left, so you normally don't really, you see some very, very tiny core in the center, like a clear zone or grain. Actually, that's a remnant A-light particle with the well-defined CSH or reaction ring. I think when you learn cement chemistry or hydration, A-light is very active, right? So produce most CSH and calcium hydroxide. So it reacts very fast. You normally don't see a lot of big particles at A-light. So you only see very, very rare remnant of it with well-defined, hydration ring, which is indicated by the red arrow. So the green arrows, you see a whole bunch of green arrows with, pointing those spherical particles, which is very typical for flash. So everybody knows flash are very, very fine, and flash has a lower water demand. Why is that? Because flash particles are very, very rounded, very, very spherical. So if you add those particles into your cement concrete, in water, those particles seems like they're lubricating the whole fluid, the whole mix. So that's why people say flash tends to have a lower water demand. So under microscope, you can literally see those rounded particles over there. So the one on the right, that's not a very normal concrete. That's alternative cementitious material. We call that calcium aluminum cement. So you see the features of the unhydrated particles are very, very different. So those are the major eliminated phases, calcium eliminated phases, in CaC concrete. So normally CaC concrete has a low, water binder ratio. So based on judging the quantity of the unhydrated particles, so on and so forth, we can, evaluate the hydration of the cementitious material. And also we can look at even the evolution of the cement over time. The one on the left is a concrete that is almost 90 years old. Back then, of course, you cannot really grind your concrete really, really fine. So you see a lot of very large, clusters of belite with pyrite. That's a very typical sign for historical Portland cement concrete. And the one on the left you see is much finer because people have done much better job to refine the particle size of cement to make it more reactive, or for the efficiency of the grinding is just more efficient. Again, I had said we can look at the flash, right? We can look at the SCMs. So the grain particles just are pointing the flash particles. So SCMs, we can use SEM to look at the details or even composition of the flash. So here, on the left, you see, actually that's a mix with Portland cement and a fly ash. So you see those kind of bright particles embedded in this dark gray matrix. Those are unhydrated cement particles. And on the left, the image on the right, you start to see the spherical particles, which are flash particles. And also you see some kind of nests, like that, some nest, distributed in the matrix that actually is, AFM or monosulfate phases. Again, so we can look at slag cement as I have shown in the very first slides, the yellow fragments here under different polarization light condition. Left is a plain polarized. You can just understand it as a very just normal light. You have one light shooting through the thin section. You see the features, the shapes, and the one on the right, you have cross-polarized light. This way we can look at the mineralogy, optical property of different minerals. So you see those particles totally, extinct, under the polarized, cross-polarized light on the right because they're totally dark. That's a feature of amorphous feature of slag cement. And these days people type 1L cement, right? So normally you don't really get more type 1-2 cement, especially here in Texas. So you have limestone in your concrete, in your cement. So here the particles, you still have cement particles, of course, the grain arrows. And also you have a lot of, limestone, fines, in the type 1L cement, up to 15%. You see a lot of those kind of small yellow or brownish, whatever particles on the right to show you the feature of limestone. Of course, this concrete has like limestone aggregates. You have some fines, from the crushed limestone, coarse limestone aggregates. But again, so this is a typical look for type 1L cement. So look at hydration. So what can we do about hydration? Normally, calcium silicate hydrates or CSH are very, very difficult to look at because they're so fine-grained. So, magnifying 600 times is not really enough to look at the individual features or shapes or CSH. But another abundant phases, which is calcium hydroxide, right? Calcium hydroxide is another major hydration product. It's a crystalline, from the reaction of cement particle with water, right? And by examining the shape or distribution or the size of the calcium hydroxide can tell you the information about the Watson ratio evaluation or the restricted hydration or normal hydration or advanced hydration, so on and so forth. So here, the image on the right, on the left, you have seen this is a plain polarized light of thin section, very, very thin section. So you can see the unhydrated cement particles, but the one on the right, we call that cross-polarized light with gypsum plate inserted. So basically, you just understand that as a different light condition to look at the features that are pasted. So in that purple or pink, images, so you can see, in the paste matrix, you have some, let's say, orange or blue, those kind of particles or whatever features, or clouds or whatever you see that you describe it crystal distributed in the cement paste. Actually, that's very typical calcium hydroxide crystals in normally hydrated concrete. And you can see this is a high Watson ratio or moderately high Watson ratio mix. So when you have a high Watson ratio mix, what does that mean? You have a very, your water, when you mix concrete at the beginning, so water is free space. So you have more higher water cement ratio, you have a higher water content, which means you have a higher free space for crystal to grow. So then crystal tend to form bigger and bigger in free space. So if you have a higher Watson ratio, your calcium hydroxide tend to be bigger. So just look at those calcium hydroxide crystals here compared to the one in the previous slide. You can see the calcium hydroxide in the higher Watson ratio concrete is much coarser. So that's another indication for us to evaluate Watson ratios. So those are the basic, examination for the components. Before I continue, I want to correct one section. So as you guys recall in a previous slide, I compared the manufactured sand to natural sand. So I said that manufactured sand is from Costa Rica, but actually that sand is from Puerto Rico. I'm very excited about Costa Rica because I'm going there shortly this week. So sorry about that typo. Okay, let's continue. So we have talked about concrete components and what we are looking at, the concrete components. Next, I'm going to go through some basic patterns for different types of deterioration. So here, I'm showing case two images from a concrete, and I think it's a concrete wall or sidewalk, I forgot. So they have the bulky freezing problem from Aspen, Colorado. So you can see on the polished surface, you see the very, very typical, the concrete top surface or exposure surface facing up. So that's orientation of these images. So you can see there are a lot of parallel cracks or micro cracks, parallel to the top surface, exposure surface. So that's a very typical freeze-thaw damage or freeze-thaw related cracks. So those cracks are generally, they go around aggregate particles, because if you think about that, freeze-thaw damage related to water ingress. So water ingress, where the water is in the cementitious material, the cement matrix. So the rocks, they are dense. You cannot have water, or very, very little water can penetrate, dense rocks, especially siliceous rocks. So you can see, when you have water, accumulated in the cement matrix, and when they freeze, and they will freeze, parallel to the waterfront, where you have the uniform water degree saturation, what we call the waterfront. So you have the progressive, parallel cracks or micro cracks. So you see most of them, they go around aggregate particle. That's one feature we identify or justify as freeze-thaw damage. Actually, I have one sample sitting on this. Literally, I have this sample sitting on my desk. You guys can pass around to see the features of microscope of the cracks. So again, freeze-thaw damage is well documented in 201. So the problem for this concrete to have bulky freezing damage is it is not air entrained, and it has a severe moisture exposure, condition according to ACA 201. So next one, we have talked about ASR damage for a while. ASR reaction is alkali-silica reaction, right? Alkali normally mainly comes from the alkalinity of the cement or cementitious materials. And the silica, where is silica? The reactive silica component normally comes from reactive aggregate particles. So we have those two components. Of course, we'll start within the aggregate or along the boundary of the aggregate. So this, they produce ASR gel. This gel is very easy to absorb moisture. So after it absorbs moisture, the volume can grow bigger and bigger. So which is expensive. Of course, different kind of ASR mechanism has been proposed to explain the damage. But again, very typical feature for ASR damage under a microscope is a crack coming from aggregate particles getting into the paste, and also ASR gel is feeling the cracks. So you see those white sector deposits on the polished surface. So the one on the left and the one on the right, actually those samples, these two images, this concrete is from water treatment plant from Arizona. So you see the ASR damage, two aggregates actually on the left, they're breaking by a crack filled with ASR gel. That's a typical feature for ASR damage when we examine a concrete sample. And the next one, again, we can use thin sections. I have some thin sections sitting on the table as well, so you're more than welcome to grab them and look at them. So we can look at the details of the ASR damage. You see those cracks getting out from a charred particle over here. The left is a plain polarized light on a thin section, as I said before. The one on the right, I'll talk about more later, that's a fluorescent light. So when you impregnate your sample with fluorescent dye epoxy, so when you shoot a black light, so you will highlight some cracks. You will enhance the contrast of the cracks or different features we'll look at. So you can see this is the same field of view, taken under completely different light conditions. So you can highlight the cracks, you can see the gels occupying some micro cracks, so on and so forth. So again, we have some current estimate standards. We have AASHTO specs. We have other industrial codes or guidance we can use for petrographic examination. But we also have some new techniques, for the examination. Here, I want to introduce maybe one, but two, but they're related to each other. We call the fluorescent microscopy and image analysis. Look at those two thin sections. As I mentioned before, thin sections are very, very thin pieces of a concrete sample, of your concrete sample. Here we have two thin sections here. You see on the left, one is kind of yellow in color, one is blue in color. So when you make thin section, always use different epoxy. You have to epoxy the whole sample to hold it together during the sample preparation involving salt cutting and polishing. So when you shoot black light, okay, you have two colors, fine, Joe. So what's the difference? So when you shoot a black light or UV light on the right, so you see one glows, one does not. The regular blue epoxy is not a fluorescent, does not have fluorescent capacity for microscopic observation, but the yellow fluorescent dye can give the capacity for fluorescence microscopy possibilities. So just by being different colors between the fluorescent thin section, non-fluorescent thin section, what's the use or the purpose for it? So the purpose is to use it for fluorescent microscopy. As I show on the right, that's a microscope with a thin section, fluorescent thin section in the middle. So you can see they are glowing. So what can we use about it? First, let's go back to the Watson ratio or cement hydration. So when you have a 0.4 Watson ratio, 0.5 Watson ratio, or 0.6 Watson ratio, like I said, same cement content or the higher water demand. So we'll give you a higher free water space in the at the beginning, and during the hydration, the increase of hydration or just the general hydration of the cementitious material. You have more, capillary pores remains, in the higher Watson ratio concrete, because you have a higher, starting free water space. So just think about that. You have different capillary pores. You have different, spaces for the capillary level pores or space. When you introduce fluorescent dye to make thin sections, your fluorescent dye or epoxy can occupy a higher volume or space of pores or space, in the thin section, in the concrete. So when you make a thin section, they're exactly the same, thickness, when you use the same light to go through different Watson ratio thin sections, because you have different pores, different amounts of fluorescent dye, so you will create different levels, let's say fluorescence. So how do you evaluate the different fluorescence levels? Just like being darker or being brighter. So here you can see those three samples images I laid out over there. So those are three thin sections with the same thickness, and also I use the same light condition to examine those three thin sections. You can see the 0.4, the fairly low Watson ratio concrete has a darker green color. So when you have a higher Wilson ratio, to 0.6, you will have a bright and brighter grayness. So why that? Like I said, same amount of light going through, but you have a higher volume epoxy can glow. So of course it will be brighter. So that can give us a, let's say, an idea to evaluate from the fluorescent perspective about the capillary porosity or the microstructure or the Wilson ratio. So again, when you think about petrography or petrographers, what are we doing in the lab? So we normally just take pictures or photo micrographs, under different light conditions, under different microscopes. When you look at those digital micrographs, actually, we have millions of pixels for each image. So we have some information that we can extract, from the images, and then we can analyze in another way instead of just using our eyes. As I have been talking about in the past 1 hour, probably you guys have got the feeling that petrography or petrographers are heavy on description. We haven't really talked about quantification. We talk about quantification, what's ratio, but I call that estimation. So can we do something about quantification? I think fluorescent microscopy can give us some possibilities for petrographers to use to quantify or better, let's say quantitatively estimate Wilson ratio. So for example, we have image here. If we extract different level, each pixel have different, let's say, gray levels or brightness of the pixel. So if you summarize that from a 0 to 255, which is a typical 8-bit image, so you will see three different peaks of pixels or brightness over there. So the lower end, the sharp, tall peak, actually that represents those dark particles on the left image. What are those? Those are some sand particles. Because sand particles, they are so dense, when you make a thin section, they don't absorb any epoxy. So when you do a UV light, they don't have epoxy, they don't glow, they stay dark. So of course you have a sharp, low value peak for the gray level histogram on the right. And also, if you look at the high end, you have a small bump, but at the higher end, like a peak over there. So that is an air void. When you say air void, so if you look at the image on the left, so you see that circular kind of bright, the bright hole over there. That's an air void. When you think about air void impregnating with epoxy, that's like a 100% free space with 100% fluorescent dye. So you have a highest, 100% of the dye occupying the space. Of course, it's very, very bright. So you have a, small peak on the high end on the right. And also between the low peak and the high peak, you have a broad peak in the middle. So what is a broad peak in the middle? That's a cementitious material matrix. So that's the matrix in the image on the left. So they're not the brightest, they're not the darkest, they're in the middle. Just because you have part of solid, you have part of it is porous. So you only have part of the space, you occupied with a fluorescent dye in this image. Of course, doesn't glow as bright as the 100% filled air void. Again, using those three peaks, we can kind of quantify probably, the relative capillary porosity or microstructure per se, within your cementitious materials. So if you have different, systems, you can compare the middle peak probably is lower or higher. So I will showcase next. So what can we do with petrographies? And I want to give some case studies for the actual projects during my petrographer like life. So first, let's say a mixed design verification or regarding new construction. So let's give a showcase or case study for that. That's a very, very basic case. I don't want to say basic case. It's a very straightforward case, but I think is a good intro to the real project. So what this case is about. So this is a facility in North Carolina, and this is a new construction. The new construction, it is an exterior slab on ground. Actually, it's a tennis court. It's tennis court. So this thing was constructed, this slab on ground was constructed in the summer 2022. So they, after the construction, after placements, they experienced some low strength issue. So, for a slab on ground, non-structural, not really. So they normally design, let's say 3,500 PSI. That's pretty normal. Western range is fairly high, 0.57. And air content 1.5. In North Carolina, it doesn't require a lot of air entrainment because free thaw cycles are not that dramatic over there. So they have low strength issue. The strength from the core samples only measured, let's say 2,500 PSI. So after, I think, a month or two. So this case, I did this like 2 years ago, literally a few months after the slab on ground was placed. So they have some good parts. They have some low strength parts, for this slab. So the client core different samples from different areas with different strength. So I got 3 samples here. And if you look at the polished slab, those are the polished sections. They all look pretty bright. They all look pretty light colored. You can't visually say they are dramatically different from each other. At least I cannot. So the air content, they are very similar as well. Like I said, I did point count for ASTM C457. Air content is not a problem. And the paste color looks very similar, on the things on the lab section. So then I want to rely on the thin sections to see if I can see any difference, among the thin sections to correlate to the strength reduction or variation. Under the plane polarized, like I said here, is a regular light going through your thin sections. So you all see, unhydrated particles. You have some B light, have the ferrite, and you have some feature, characteristic difference here, but it's not very systematic. It's more probably because, the sample prep for the thin section not perfect, or just some localized, variation of the thin section along the plane polarized light. So the regular plane polarized light observation cannot really tell a lot of story of it. So then I look at them under fluorescent microscope, fluorescent light. So this is 100x. So this thin section, again, they're similar in thickness. So when you shoot the same light, you take pictures and same light, they glow kind of differently. So you can see the higher Western ratio one kind of darker in the color, and the low strength concrete has a bright, let's say, green color in the image. So then, like when we use those, histograms to calculate the peaks and different values, right? So we can come with different numbers. We can call that relative capillary porosity or microstructure or some name you want to say. So you can correlate the strength with the calculated, let's say the relative brightness or capillary porosity. So they are well related. So you can say the water probably was off from the mix design. So I know we're still in the school, but when you go into industry, especially to do consultation, engineering consulting, you will run into a lot of problems with water variations for new constructions. Additional water is always a problem for constructions. So probably you have low strengths and you don't want to justify the slump, and you have other, issues. Probably you got delayed delivery of this truck. You don't want to reject it. You want to add more water to rework it and to pump it and finish it. All the kinds of, variations or reasons can introduce, water at different times of the construction. Sometimes, if the truck has some tailwater, when you batch the concrete in the truck, but the truck got cleaned out the day before, but they have some tailwater sitting in the tank, in the drum. So your water schedule can be off too. So there are so many different ways to add water during construction. So that's why, as an engineer, as a material scientist, we have to be very familiar with construction applications or how we do that on site to trace back what's the reason for different problems. The second one basically is a surface defect issue. So this is ring damage. So this one I think is more related to transportation, because we're transportation, center, research center. So this is construction years ago. It's an interstate highway bridge in Utah. The contractor was placing 3 bridge spans. So a thunderstorm came in, and a heavy rain with, I forgot was a period, but hit the newly constructed or placed bridge spans. And the Utah DOT said, we want you guys to look at the samples to see if the concrete has been severely damaged during rainwater. Why rain damage is important, or sometimes cause damage or defects to your concrete, because new concrete, because it literally alters your surface water ratio, right? You have more water get onto the surface, right? So if you have a higher water ratio concrete or paste on the top surface, it's a pavement. So you are worsening the wear resistance of the pavement, which is the most important thing for a pavement. So that's important. And okay, so the DOT want us to look at, okay, what's the damage extent? Okay, from this rain damage, because they have to do some repair maintenance. Probably they need to grind off the top surface, do an overlay or whatever, but they need to know what's the damage extent for this. Design strength 4,000 psi, water ratio 0.4, air content 6%. You can say here 6% because in Utah. So air, free thaw damage is important. They need air entrained concrete. So the rain damage, like I said, so rain damage alters the surface water ratio, right? When I mentioned water ratio, the first thing you want to examine is the color variation. If you have a higher water ratio paste, your color is brighter, right? So if you look at there, I don't know if you can see clearly or not because of light, but you see those red bars, compared to the paste in the middle, you kind of see it's brighter over there, at the top compared to the middle of the unaltered concrete. So that's the way for us to examine, the rain damage extent, just by examining the color variation, the hardness variation. And this is more pictures about the lighter paste and the regular color paste. So the rain damage from this case, I think, is very limited to 1/16 inch to 1/8 inch. So not too bad. And also from the fluorescent microscopy, you can see the difference as well. So you see, the one on the left, that's the top surface. You see much brighter compared to the middle of the concrete. So the same light condition, but it's much brighter, a much higher water ratio. It's altered. And the rain damage, like I said, only impacts the top surface region. But how do you prove that like the majority of the concrete has not been impacted by rain damage? So a very interesting thing I think I did first, of course, you can measure the strength, right? So we sent some samples for compressive strength testing for ASTM C452, C42, sorry. The strength is very similar from each other. It's way exceeds, designed 4,000 psi. And also, we use the bottom part of the concrete pavement. We run the resistivity measurement. So the resistivity measurement, I don't know how familiar you guys are with electrical resistivity of the concrete. So basically, it's an indication for the transport property or the concrete quality of the concrete. So they have the similar bulk, electrical resistivity among the damaged or undamaged, the concrete bridge spans. So that tells the bulk of the concrete, they're still intact, not altered by rain damage. The rain damage only limited to the top up to 1/8 inch. That is, small case about rain damage for during bridge construction. And the last one I want to showcase is free thaw damage. During my postdoc or PhD study in this country, I did a lot of de-icer damage studies, and one major study is a I think it's chemical/physical alteration by de-icers. We call that de-icer damage. So people use a lot of de-icers in the north, up in north. So a lot of de-icer, we know they're chloride-based salts. So because salt can lower the freezing point of water, right? So sodium chloride, we call them rock salt, is mostly or widely used de-icer salt. But to improve the efficiency of the salt or the melt, the sort of lowering the melting point of the water or freezing point of water. So actually calcium chloride or magnesium chloride are way more efficient than sodium chloride. So people use more and more use, or DOTs use more and more calcium chloride or mag chloride for de-icing or anti-icing purpose, mainly de-icing. But the problem, one reaction can occur, especially in a low temperature range. So actually the calcium hydroxide, as we say, is a hydration product from cement and water during hydration. So in a low temperature, it can react with calcium chloride, which is major chloride-based salt, with water. So it can create a, we call that, complex salt. So we call that calcium oxychloride. It's a salt. So what is the salt? You see these two images here. The one on the left, I took that outside my hotel in Chicago 2 years ago. This salt, if you have a lot of salt accumulation at the joints, because you have poor draining at the joints, it's a little like a tiny pond. So you have salt, you have water, you have low temperature, you have calcium, hydroxide. So a lot of times you have this premature joint damage. So this is joint damage. You see the majority of the slab is okay, but the joints are kind of deteriorated. So they're missing, they're crumbling. So a lot of times these are de-icing salt damage. So if you ask Joe, have you ever seen or observed this salt, in real case? It's very, very difficult to see this salt directly. So this salt involves some, let's say, phase change material, or it is only stable under a low temperature. Let's say when the time comes to spring or summer, so this salt will decompose back to calcium chloride and calcium hydroxide. So in the summer, during maintenance, you cannot really directly see a lot of this salt. So this case is very interesting. I think I'm kind of proud of it. So this is a case I did like 4 years ago when I was back in Colorado. An engineer, city of Denver, they do maintenance for their public transportation centers or stations every year because snows a lot there. So the winter condition is critical, and their performance is very critical. Their public infrastructure. So the engineer were on site. It's a 5 years old platform, in a train station. After they review the yellow warning stripes, right? That's on the platform. So they see this kind of very white and crumble or like mud, like concrete underneath this warning stripe. You can see they are almost kind of white over there. They try to core sample to me to let me examine what concrete is and what's condition concrete, but they basically cannot core sample because you can just use your hand to grab it. That's 5 winters after the construction. So the engineer collected some samples to me, and I look at it. So of course, the concrete has some problem itself. So it has a very high Western ratio. So I have a sample sitting right there. So it's very high Western ratio concrete, has no SCMs. In this severe free thaw exposure condition, that's not allowed, or that's not consistent with ACI 201 or even 318, and inadequate air entrainment. So you have a lot of high chloride exposure because you apply a lot of de-icers to the platform because you don't want any passenger to slip. You want to guarantee the public safety. The sample was so crumble or so muddy, so I can't directly cut or polish sample because they're so soft. And I use epoxy to stabilize the pieces I got. So after I use epoxy to stabilize the pieces, so then I can cut and polish the sample. You can see that's a polished section surface right on the left. And you see a lot of cracks. You see a lot of parallel cracks, horizontal cracks. That is very typical to the free thaw damage I mentioned a few slides ago, a few slides before about free thaw damage. And also you have some white deposits. You see the crack there filled with the green epoxy, but they have some white stuff over there. We call them deposits. So that is actually, calcium hydroxide blended with calcium oxychloride in those minerals. I will show you later. And also I measure the chloride. So they have a good sample, they have a bad sample. The good sample is under a shade. They don't really apply a lot of deicers, but the bad ones like under the warning stripe. So they apply a lot of deicers. Of course, you see a dramatic difference of chloride content on the right. So also the engineer asked me, can you just do some quantification to justify the damage? I think probably I can. I'll try. This is the polished section under UV light. You have seen this, right? So you have glowing cracks filling with epoxy. You have the darker parts of the paste that is not very super saturated with epoxy. So we create this kind of contrast, right? Use some basic image analysis tools. Actually, you can identify those cracks on, in the middle. I didn't draw the lines myself. Those red lines, actually, they were automatically identified or detected by a software. So then we can summarize the orientation of the cracks, which is the rose graph on the right. You see they're mostly horizontal, right? After we identify the cracks, you can measure the crack length, you can measure the crack width, you can kind of come up with the idea about the cracking density or the damage level. So you can see, when in the region near the top surface, you have more damage, and we call that upper zone or outer zone or lower zone or inner zone. And also, you have more cracks, so you have a higher crack density, you have a higher cracking area in the upper zone or the outer zone, which have the most free thaw damage, because water or de-icer ingress follows the diffusion or transport from outer to inner. So of course, the outer your location is, the more damage you will get, and you can quantify by using some basic image analysis here. And also, when I look at the pieces, like I said, they're pieces, they're not really a core, right? So you see this piece. So this piece has like a kind of white crust on the top. You see on the image on the left. And also when you break a fracture surface on the right, you see some clean crystals, clear crystals, very well-shaped crystals lining the fractures or cracks. Just based on this hand samples or the stereo microscope, you can't really see or tell what they are. You can only see the color or the transparency. So then you can use SEM. You can use SEM to look at the elemental composition of the deposits you are interested in. So I break a piece of sample and put into the SEM chamber. I found a air void. So the image on the left, that's a fracture surface, that's an air void. You see this air void is filled with all different kinds of crystals, right? They have some needle-shaped ones, they have some plates, they have some longer, elongated, or layered samples. So I identified 3 different kinds of crystals filling this air void. Do you follow? That's an air void, right? So when you analyze the elemental composition, so look at, point A is the blue line, the EDX spectrum on the right. So you can see there's a peak of calcium, there's a peak of chloride, and there's a peak of oxygen and carbon. Carbon basically is something got carbonated out over years. So you have these 3 elements. That's a very direct indicator of calcium oxychloride. We're talking about the complex salt. And also, you see the orange point B, you have a lot of calcium, you have calcium peak, you have a sulfur peak, you have aluminum peak. So that is, what is that? Based on the needle shape, we know Eschingite is like needle-shaped minerals, right? So that's an Eschingite crystal. And what is a C? C only have calcium peak, you have oxygen peak. That's calcium hydroxide crystal. Why do you have calcium hydroxide crystal? Like I said, calcium oxychloride is metastable or unstable when the temperature is above a limit at different solution, concentrations. So your oxychloride can be easily or readily deposed to calcium hydroxide and calcium chloride. But calcium chloride is very easy to dissolve and run away. So calcium hydroxide sometimes can stay or leave there. So 3 crystals are identified in this case. So that's a very typical or direct evidence of the presence of de-icer damage from the de-icing salt. Also, calcium hydroxide can react with calcium chloride. So when you think about that, calcium hydroxide can be extracted from the paste matrix and redeposited in the voids or in the cracks. But will that make your concrete more porous? Because 20 to 25% of the paste volume is made of calcium hydroxide. If you have all those crystals gone to react with the de-icers, so literally like your bone is losing calcium, make more porous and is more prone to fracture. So the same deal to concrete. You have a higher porosity, matrix porosity, you have a lower mechanical property, right? So how do you identify that? So you just find calcium hydroxide. So you can see the good mortar on the left and damaged mortar on the right in the same facility, different regions. You can see completely depletion of calcium hydroxide on the right. Those crystals like orange or blue, as I mentioned before, those are the crystals calcium hydroxide, right? The one on the left, that's a good mortar without chloride exposure, but the one on the right, that's a lot of damage from the exposure to de-icers. Your calcium hydroxide is completely gone. And you can use softwares to segment different colors or features, by machine learning or some technologies. You can quantify, the volumetric or the area percentage of different components. Literally here, we focus on calcium hydroxide. And you can see the huge reduction, right? From the image, yes. And also by the software analysis, you see like almost 90%. That's almost all gone. So that's a lot of capillary pores are opening up, are more available, to lower or worsen the mechanical property. Again, capillary porosity under fluorescence microscopy, we see the direct difference, right? So you have a higher porosity in the damaged mortar because calcium hydroxide is leached out or reacted out. So you have a brighter green color on the right. Good mortar, you have a regular, let's say, a darker green color. You do a calculation. And in the same, let's say, the light condition, you see the lower peak for the air gates, they're almost very similar, right? And the peak for the air voids, they're very similar too, but the middle peak, you see, is shifted from a lower region to a higher region, from the good to the bad. So that is a way for us to at least semi-quantitatively, characterize your material with fluorescence microscopy and image analysis. So those are the 3, let's say, case studies during my, petrographic, career from different aspects, new construction, low strength issue, surface defects, rain damage issue, and also, durability issue, like this freeze-thaw damage. And I want to talk about what is really the future of petrography. So in my past, let's say 1 hour and 45 minutes presentation, I'll talk about, you can tell it involves a lot of experience or training. It does. If you go to ASTM C.E.A.T.E it says a junior petrographer needs a supervision of a senior petrographer for 5 years before they can independently examine the samples or sign reports or issue reports. So it's a long training session. And there is no specific major to target concrete petrography because such unique expertise or technology. A lot of petrographers have a background of geology and then get trained by senior petrographers to get information or knowledge about the concrete and then turn into a concrete petrographer. So that involves a lot of, human to human training or experience. But in the future, I want to say the job of a petrographer is mainly we use our eyes to identify different features on a poly lab section, on a sample section, or on a thin section. But when you think about that, can we just use computer to do something like that, or just we train computer or programs to say, okay, we don't need Joe is sick today, so can we still do this job, right? Or can we do this job in a better way or faster? I think people have tried, researchers have made some progress in this. Here, I want to, of course, I am not a computer scientist. I don't really know a lot of details about the processing, yeah, this or that. But I believe image analysis with, machine learning or artificial intelligence in the future could shed a light or be a big assistant to our efficiency and accuracy. Here, I want to give a one quick study, like a look about what people have tried to achieve with machine learning and artificial intelligence for image analysis on concrete studies or petrography. I think some researchers have done some research about how to use computer programs or machine learning techniques to automatically identify the air void, air void systems. So, like I said, the air void system analysis are very critical to freeze-thaw damage and inadequate or improper air entrainment air system are, let's say, like insufficient to freeze-thaw resistant. How do you characterize that? Right now, what we do, we have a standard ASTM C457, right? And we publish section, and the petrographers can sit in front of the computer to do the point count. That's what we do. What we say, you count, 1,000 to 1,500 points. Each point on this slab surface, is an aggregate, is a paste, is a void. So then you do this calculation about air content, paste content, aggregate content, basic idea like that. But I can tell you, it's a very tedious, it's very painful and time-consuming process. A petrographer for complete air void analysis with spacing factor surface area, it at least will take you 1.5 to 2 hours nonstop in front of the microscope. You have to look at a microscope and do a point count. So it's not super efficient, a very manpower consuming, time consuming. But in a machine, let's say if you try to train, your computer to learn what is an aggregate, what is an air void, what is a paste region look, like under microscope or in this image. After rounds and rounds training and learning, probably the computer can eventually pick it up and do the job for you, and you can get it done maybe in a minute. So this is a research, I think, by some researchers from University of Illinois a few years ago using image analysis to identify air void systems. And you can see the results is very satisfying. So they can even identify the imperfection in the limestone rocks. You see, to enhance contrast, he used, some pink powder to fill the air voids, right? To give you the enhanced contrast for the computer to better pick what is a paste, what the air void will be purely pink. And you see there are some imperfections or spacings in the limestone particles, right? They're filled with some pink powders. We don't want to count those imperfections with the chalk or the pink color. So with the machine learning, they can learn what is a real air void, what is an imperfection filling in aggregates or in the paste. So you can see here, so the machine learning, the program can give you, okay, that's an aggregate, especially the particle on the bottom middle, right? They have a lot of pink powder, but the computer can identify after training that the aggregate, that's not real air voids. After, this analysis can only take, let's say, 1 minute. So maybe sample preparation will take you, let's say, a technician 10 to 15 minutes, and then you scan the image, but then after you feed the image to the program, it will take minutes instead of hours for such processing. So that's a big, let's say, liberation, of the manpower, the time-consuming process manually by petrographers. I think that's very promising. And that's just one case I want to talk about, the possibilities in the future. Probably, I think computer can hugely assist, petrographers on our job, our judgment. I know it's a very specialized, field, for such work to be done compared to, let's say, the medical, the hospital research. But I hope in the future researchers can keep working on push this effort to the industries to better assistance in industries. And also limitation, I want to go through this. Of course, one thing, we can tell you a lot of different features of concrete in the past 2 hours, but also, like I said, quantification is a problem for us. I don't want to say it's a problem. Quantification is very, very challenging, especially Western ratio estimation. So we use, different aspects of paste features. We use, fluorescence microscopy. The whole purpose for different techniques, we want to better quantify Western ratio. And I think, quantification or image analysis should be better or further improved or developed in the future to help us or help industry to better assist the troubleshooting process. Also, petrography is a little bit time and labor consuming so far, and we also, it's kind of expensive option for troubleshooting for a lot of cases, but I think it is necessary for some case studies. If you really want to troubleshoot what has happened to your material, you want a satisfying or, let's say a comfortable or confident solution for your repair or maintenance in the future. Sometimes petrography is, you cannot avoid it, even though it's expensive, but it's in a lot of cases, it's the only way to tell you what has happened to your material. And that is mainly what I want to convey in these 2 hours. Again, we are one team player for the whole forensic, investigation with engineers. Teamwork is very, very important. And also communication between different parties, between engineers, petrographers, between clients and petrographers are very critical. The more information we know, the more information you know. And also, I just cannot address more about collaboration, teamwork, between different parties in real jobs. That's very critical, for our industry and the community. And thank you very much for everyone. Yeah, yeah.
Okay. Thank you so much, Dr. Chow.
Yeah.
Thank you again. We do have about 2 minutes, so we can have maybe 1 or 2 quick questions. Do we see any questions online? We don't have anything online. How about here? Okay, I probably can ask a very quick question. So
Sure.
I'm just curious, what if I want to create my own lab? What basic equipment I need to purchase in order to perform very basic petrographic analysis?
Well, that's a good question. I think a lot of lab preparation requirements or accessories has been described in ASTM C.E.A.T.E 856. But basically, I think you need a saw to cut your samples, right? So we can see that requires a lot of cutting or saw cutting, water saw or oil saw, and also you need a lap section, you need a lapping machine to get a polished surface. And for the thin section making, if you don't want to outsource your thin section making to other parties or companies, you need a thin section machine to make your own thin sections. That's a sample preparation. I think for the examination, you need a stereo microscope, like the reflective one to look at lab section. And also you need the microscope right now in the slide. That's a petrographic microscope to look at the thin sections. I think that will be the basic setup for a petro lab. And other than that, maybe just a very small, accessories about, the needles for different Mohs harness or a color chart. You need a good camera to capture, the images you want to take from the microscopes. I think that's basically is a petro lab, need, for study. Yeah.
Okay, and do you have a rough number, how much investment, just roughly, or?
Oh, that range, because each equipment can vary so much, from different qualities or different accuracy. Even microscopes can vary so much, from price, from 10 grand to 20, 30 grand. And a lapping machine, I think, I don't have a number in the top of my head, but I can discuss with you,
Okay.
after this. Yeah.
All right, cool. Yeah. Oh, there are 2 questions. Oh, okay. We can have maybe we can
Sure,
have
go
the
ahead.
question.
Yeah.
Can you please or the project was just to identify the problem?
So, that really depends on the scenario, the projects, also the structures. For example, if we talk about ASR effective dam, that's a big infrastructure. Any change or demolish or any big up, maintenance for a dam structure like that big, involves a lot in the decision making process. It's a lot of budgeting. So for a case like that, it's more like yearly, routinely monitor the progress of ASR and inform stakeholders or government or agencies to plan ahead, for the budgeting in the future, what's the prognosis or what's the rough conservative, remaining service life, for those structures. I think ASR is such a unique problem. We call, there's a reason for us to call that ASR like concrete cancer, because it will just, once it's triggered, so it will just keep going, and keep expanding. For small structures, let's say a residential pool, if you have a pool with ASR in your backyard, that's a small project. And also, for example, here in Texas, the summer is so long, the temperature is so high, that can promote, ASR reaction. And also, we do have a lot of reactive particles or agates locally here available in Texas. So everything just will make, some water structure like a pool very, very vulnerable, to ASR if you don't do a good job on, the material selection. For cases like that, once ASR has triggered and started to show cracks, and probably you need to start to talk to your insurance companies or any other parties for demolition or rebuild, because there's no, so far within my knowledge, I don't think there is very efficient or proper way to repair ASR structures. So we can only say we can closely monitor the progress or development of ASR damage and make plans for the future. But when you say high save ASR structure, it's very, very dangerous. It's very, very challenging, even for bridges, let's say highway bridges, that is away from above ground. But sometimes the internal moisture level can just be fairly high for a long time, just keep the ASR reaction ongoing. So again, close monitoring, early identification would be my advice, for ASR projects, and recognizing the ASR progress by petrography is important for the planning for the future, but repair is very, very challenging. It's really a case by case study. There's no generalized answer to that. Yeah.
There's a second question raised by the same audience. Could you please share some details on how you do L void percentage using HTMC 457 or others?
Yeah.
How did you do the calculation and the WJE, and how much area do you observe from the representative area of the C section to calculate the spacing factor?
ASTM C457 had very, very specific requirements for the areas you want to analyze and how you do, the airborne analysis. There are three major methods for ASTM C457. We call method A is a linear traverse method, and we do method B is a point count method, and method C is a enhanced contrast method by, flame bed scanner. So in WJE, we normally do method B, which is the point count method. The point count method basically is you have lab section for, from your sample, and you decide, the specific area you want to analyze based on the standard. And also then we use a computer programs to put our sample to calculate the spacings we want to do the point count. And we have XY auto stage with a controller, for the point counts. So we just evenly distribute the required point counts in the specific area required by ASTM C457, and start to do the point count just on the computer. So finally, we summarize, how many points we run through by the linear, the traverse lines, and also what's the total aggregate point stops for each point, what's the pace to point count, the point counts, air point counts, and total air point counts, and we do the calculation. So yeah, so everything has been very well defined in STM C457. And also the bias and the error or the accuracy has also elaborated in the last section of the standard as well. Yeah.
Thank you so much, Dr. Chow. I think with that, we can conclude our morning session. Thanks everyone for attending either face-to-face or online.